All right, so the power rule for positive integer powers of x. I wanted to walk through the proof because I think this one is pretty interesting and elegant. And many of the things that I talk about, I'm just going to show you them rather than prove them. So we're trying to find given this function x to the n, where n is a positive integer power, find the derivative. We want to prove that it's equal to n times x to the n minus 1. So first thing we're going to do is say, well, the definition of derivative says that the derivative is the limit as h goes to 0 of that difference quotient, x plus h to the n minus x to the n divided by h. The binomial expansion using Pascal's triangle, and in fact, I have a video about that, says that x plus h to the n can be written as x to the n plus n x to the n minus 1 times h plus, and then what we notice is that x power keeps going down, h power keeps going up until we finally get to the last term, which is h to the n. And I just wrote it, instead of writing it all out, we've got stuff times h squared plus dot 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 plus h to the n. And that power of h will just keep increasing until you get to n. Now, why is this important? It is important because the definition of derivative says that if I am taking the limit as h goes to 0 of all of this, x to the n plus n x to the n minus 1 h plus stuff h squared plus dot 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 plus h to the n minus x to the n all divided by h. Well, if I do a little simplification, what we discover is that this x to the n and that x to the n will cancel each other out. And when I divide everything out by h, this h goes away. That becomes plain old h. This becomes h to the n minus 1. Everything in here will still have a power of h. So what am I left with? I am left with the limit as h goes to 0 of n x to the n minus 1 plus a bunch of stuff with h's. These all have h's. And as I take h to 0, those all go away, and I am left with n x to the n minus 1. Elegantly and beautifully proved. Not by me. I'm just telling you how it went. All right. Thanks for watching.